Joining us online, we're going to have now an international perspective to this sequence. We're going to talk about modeling the Gulf of St. Lawrence with AI, and Francois Roy will be with us online. There he is. Thank you very much. We're going to talk about this Gulf of St. Lawrence with AI. Thank you very much for being with us.
Thank you. Do you hear me okay?
Absolutely. We hear you and we see you, and I believe you might have slides that you might switch yourself, or we are ready to listen.
Yes, I'm going to say next often, but yes, I'm going to talk today about the Gulf of St. Lawrence. Actually, the Gulf of St. Lawrence is kind of an all you can see in terms of physical process of ocean circulation. So, and like Anas mentioned in the roundtable, we rely on the physics-based modeling to train the AI for these kind of coastal environment. And the Gulf St. Lawrence physics-based model were developed. It started like 30 years ago, and I was part of these 30 years, and I was kind of curious of how machine learning could handle this complex environment without data. And yes, so next slide, please. So the context here is that we don't have a lot of machine learning applications with hourly time steps, including the tides. And like I said, the Gulf of St. Lawrence is very complex. It has tides, estuarine circulation, strong seasonal cycles, evolving stratification. So we have 3-layer stratification in summer and 2-layer in winter. We have steep topography, sea ice, internal waves. So all of these features will affect the surface current in particular. So I'm exploring how machine learning can emulate sea surface height first and currents, including the tides. And I'm also exploring how to separate the surface current into barotropic, baroclinic to help the machine learning training. So next slide, please. So this is the domain. The main domain of our emulator for now. It's a 136-degree resolution data set for the training over this Gulf St. Lawrence region. And we're also planning on doing downscaling applications at 500 meters and 200-meter resolution. Next slide, please. So this is here an example of an animation of the surface current, the U component of the surface current. As you can see, it's quite dynamic. So this is the total U surface current. So next, please. So depending on the region you're in the Gulf St. Lawrence, you have more barotropic or baroclinic surface current. What I mean by that is that in the top of the estuary here, you'll have more barotropic current in the sense that it's close to the vertical average. You can imagine the water column moving up and down. And here it's a larger, close to 2 meters per second amplitude. And if you go next, please, we can do next, actually. So in other regions, more in the Gulf regions, you have less important tides, and you start having more like a wind-driven process or storm surge coming from outside or locally driven by wind. So you have more complex signal. And I'm going to try to decompose the signal here. So if we go next and next. Again, okay. So here, what I do is I look at the vertical average of the water column, the U component average over the water column, and as you can see, there's still a lot of so it's mainly driven by the boundary. If we go next. So most of this energy comes from the outside of the picture, if you think in terms of machine learning. and it's driven barotropic part, so the large-scale tides. So if we go next. Now, if we remove this barotropic component from the surface current, we still get a lot of tidal energy, as you can see on the bottom left. And this tidal energy is mainly locally driven, so it's like rectification of tides from stratification or bathymetry effect. And also in this baroclinic part, the residual, we also see local surface wind events. And so the important thing here is that you for this baroclinic part of the tidal energy, you cannot do an harmonic analysis because it depends on stratification, and the stratification evolves with months and seasons and climate change. So that's why I decided to include the tides in the machine learning process instead of trying to predict it with harmonic analysis. Now, if we go next, we're going to have like so this is the daily mean of what you see on the bottom left. So it's kind of, you can see like the large scale density flow, more like the slow circulation. And as you can see, this is one of the challenge we have because at depth, we usually we have like 3D average outputs. So we kind of missing a lot of tidal energy. That's one of the challenge we have for training. So next. Yeah, so if we were to separate the circulation at depth, we would have to do an approximation like it's. Go next, please. So I've been using two different machine learning models. So the one on the left is the LSTM-based model. It's more like an in-house model, and on the right is the well-known Animoy developed by ECMWF. So next. And next again. So just the basic difference between the two is that the one on the left is more time resolution focused, and the one on the right is more spatial resolution focused. And of course, it's much more powerful because it's community supported and it has a large team working on it. Next, please. So we've been doing a training based on our physics-based ocean model simulation. So we have a 30-year simulation and an independent period for doing inference. So I will present just summarize results from 4 experiments, one with the LSTM-based model and others with different configurations of Animoid. So our model truth here is the COPS is Canadian Ice Ocean Prediction System. It's our operational system at 136-degree resolution. So that's the one we're using for training as well as for evaluation. Next, please. So this is just an example here. Next, please, of results for tide. So what we do here is we assemble short 24-hour forecasts and create a time series. So the model truth here is a blue curve hidden somewhere behind all the other curves. The other curves are produced by emulators. So what you can see here is that the emulators can understand the tides and the different modulation of tides, so neap spring cycles during a year, and also other astrophysics related modulation. Next, please. So from a monthly perspective, you can see nice neap spring cycles understood by the machine learning. And next, please. If you look at it from a weekly perspective, then you're starting to see like subtle differences between the curves, and these can be explained by the methodology we use in machine learning. So next, please. So apart from the tide, and next again, we can see also subtle surge here at the station. So the station is near M2 Amphidrome, where we have weak tides. So we have these small surge popping up here. Next, please. And you can see that So again, machine learning can understand, so it's maybe external forcing or maybe local wind-driven forcing that is captured here by the machine learning. Next, please. So the future challenge, next please. Here is an example of a 10-day forecast I did with Animoy. So the advantage of Animoy is that it's auto-regressive. So once you've trained it and you have your forcing available, you can do a forecast of any lead time you like, and it's really not expensive. So you can go like, I could have done a yearly forecast without any cost and here. But the challenge here, if we go next, please. So this is like sea surface height predicted by Anemoy, and you have the model truth in blue and the currents. And you can see here at 72-hour lead time, it starts to drift. So that's one of the disadvantage of the auto-regressive approach. So the next step, so next please. So next step for us is because it's a technical thing here, but Anemoy was designed for atmospheric forecasts, and we need to adapt it a bit. So for our coastal and ocean environment to have the boundary forcing. So the idea is to cope with the error growth so because in animal you have two types of variables, you have the prognostic and the forcing types. So we could have more forcing type variables to constrain the coastal system better to have a longer lead time. So that's what I will do next. And we want to increase the lead time, like I just said. We want to extend our applications to ensembles, increase the domain size, for the 3D currents, we won't have a pre-training strategy because we cannot save like hourly outputs 3D. It would be very hard to manage. So we could do shorter runs for fine tuning with the barotropic baroclinics separation I mentioned earlier. And we want to go for more detailed evaluation. And one thing that interesting for us, is the chaotic aspects in the Gulf of St. Lawrence. We have a lot of chaotic flows in the density-driven currents. So it seems that machine learning is kind of naturally capturing that by not understanding. So when you have chaos, you have like less repetition in this kind of scenarios you see. So by not understanding, it's like machine learning will understand or not understand that not knowing what to do will create some natural chaos, to my opinion. So it's kind of interesting to when we want to look at ocean model uncertainties, for instance. And then we have these downscaling application that could be very interesting because for very cheap computer costs, we could do a very high resolution. And as far as the resolution increase and we get to a more constrained domain, I think it's easier to the complexity of the current might reduce and it might be more channeled by topography. It might be quite interesting to develop these applications. So thank you.
Thank you,
That's
Francois.
for me.
Thank you, Francois, and for diving into the technical details of these models. And now I'm external in terms of the expertise. If I use the wrong technical jargon, please forgive me. That was interesting what you said about the chaos of the tide movements and its composition of the St. Lawrence Gulf. Correct me if I'm wrong, I would have thought because of its algorithmic functioning that AI would have trouble following that, and you're saying it's the opposite, it's that it's actually helping to follow this chaotic aspect of the Gulf? Or is that a case for the continuous and enhanced interaction between natural intelligence and artificial intelligence, which is necessary for the St. Lawrence Gulf?
So what I meant actually is that when you train your system, these chaotic scenarios will create something that will not repeat often.
Okay.
And so when you do your inference after, the model will have the machine learning model will have a lack of precision and will do maybe more random
Mm.
prediction for these regions. Look like we have a Gaspé current along the Gaspé Peninsula, and there's a lot of wiggles and chaos. So the fact that you train it with like a 30 years period, but these kind of scenarios don't happen the same time, the same way, the same time. It's kind of like for me, I see it this way. It's like it will produce some random solution, but anyway, we know that our model is probably wrong at this place anyway because it's chaos. So it's probably not close to observations. It will generate its own, even the physics based model will generate its own chaos.
Thank you very much,
I don't know if
Francois.
it's clear.
No, thank you very much, Francois, and stay with us because we are going to continue the discussions.